Today I would like to talk about our recent experiment about time-being encoding on a satellite link. And let me just give our motivation for that, why we want to have satellite communication. Essentially because free space link is necessary if you want to go to real long distance. We all know that the fiber link transmission scale exponentially with the link length, while let's say in vacuum propagation, you have a polynomial scaling, this quadratically, with the distance. So, for instance, in a 1,000 kilometer link, in the standard fiber, you will have 200 dB of losses. That, of course, is no way to do QKD. On the other hand, with satellite, you can get up to, let's say, 50 dB. This is our typical result. But you can even go lower losses. If you optimize optics, you increase your telescope. So at a larger distance, there is no way to go to fiber. You need to go to free space, of course, without quantum memory. And of course, there is another physical motivation that with satellites you can explore quantum mechanics at a very long distance and a very unexplored scenario. And of course, the research in this field is very active. There are already two satellites were launched for quantum experiment, one from Japan in 2014, and last August was launched the other satellite, but they are not still working at, let's say, to the quantum experiment, and they are ongoing program in the world, Canada, Singapore, and okay, so let me just review what is the general scheme that we use to test this quantum communication link with the satellite. Essentially, without a source of a quantum source, what we can do is to emulate a single photon source from a space by using a kind of plug-and-play scheme. Okay, it's a plug-and-play scheme in free space. You send a strong laser pulses from the ground station. Okay, you have on the satellite, you have the so-called corner tube retroreflectors that are spatial mirrors that reflect the light in the same direction in which the light comes from. And so, due to the losses in the uplink, you can emulate a single photon source, let's say a coherent state at a single photon level that is coming from the satellite. Okay? And the typical downlink that we measure with a 3 centimeter corner tube, the descending light from the satellite, is in the range of 50-70 dB. Okay, so this is a typical scheme. Strong laser reflected from satellite emulate the single photon source. And the observatory that we use for our experiment is the Material Laser Ranging Observatory of the Italian Space Agency. And essentially, these facilities was mainly essentially built for satellite laser ranging. Okay, so they are measuring the distance of the satellite by using time of flight measurement of the light. Okay, and our scheme is to essentially overlay the satellite laser ranging pulse with our, let's say, qubit pulses. Okay, we have these strong laser ranging pulses that are 100 millijoule, very, very energetic, but very low frequency, with very low energetic pulses at much higher frequency that when reflected from the satellite will become our, let's say, qubit source that is coming from the satellite. So both beams are sent to the telescope and they are received back. And indeed, the telescope used in both directions. The outgoing beam is sending through the telescope and it also received back through the same telescope, and a simple beam splitter separates the outgoing and ingoing beam. Okay? And one technical detail is we use large area photomultipliers that are designed to address for velocity aberration, because when the lights come back there is velocity aberration, so the light is slightly tilted from the direction you send it. Okay? And we use 81 picosecond time tagging. Okay, so this is the main ingredient that we use, and with this scheme, we have shown the polarization encoding from the satellite. Indeed, typical as Thomas was explaining, polarization is the very easy encoding for free space communication. And indeed, what we achieve this is a figure of a single passage of a satellite. This is the distance of the satellite from the ground station, and this is the time of the passage. And we use this satellite. This is a 24 centimeter. It's a ball, 24 centimeter is a passive object. And what we did is sending to the satellite different polarization states and measuring in two orthogonal states. Okay? And what we show is that by sending HV left or right polarization state, we were able to discriminate what are the sent polarization. We send H, we detect only H. We send V, we detect only V. Okay? So the 4 polarization states were received in a 10-second window, okay, with an average covariance of 6.5%. Okay? This is compatible with the limit of QKD. Okay? And we repeated the experiment with several satellites. I show the result just for, let's say, a V polarization state. And you can see that only the V detector clicks and the H detector almost is dark out. And this was performed with several LEO satellites, low Earth orbit satellites. And all the signal was, let's say, was detected within 1 nanosecond time windows. From the types. Indeed, the temporal synchronization is crucial to precisely address what are the real photons coming from the satellite from the dark count on the stray light package. Okay? So this was the result for polarization, and we also have a result to, let's say, extend the communication to the MEO satellite that is medium Earth orbit. We did not have polarization encoding in this experiment because this satellite has not polarization from preserving corner cube. This is a technical detail. However, you can here in this picture we have the distance are all in scale. Okay, so these are the LEO satellites. These are the distance from the Earth compared to the radius of the Earth. We want to go farther, so we went to Lagos. That is 5,600 kilometers. Okay. And we achieve a single photon return from the Lagos. Okay, this is again the passage of the satellite. The distance goes up to 7,000 kilometers, and you can clearly distinguish the single photon return from the background. In this case, the signal-noise ratio, of course, is lower because there are much more losses. But you can clearly see that the timing uncertainty are completely the same, and indeed are only due to the jitter of the detector. So is intrinsic detector is due to the detector. Okay, so can we go farther than polarization? Yes, as Tom was explaining, we can also use time beam encoding for free space link and towards satellite links. And indeed, what we had in mind is to use an unbalanced Mach-Zehnder interferometer to create a superposition between two pulses, here late and early pulse. And you can encode the qubit in the relative phase between the two pulses. Okay? And by using the same scheme, we want to see if this phase encoding could be preserved. Okay? And there are two main issues. One is turbulence, okay? Is turbulence detrimental for such encoding? And the other is this encoding stable over such long distance and also with moving object, okay? These are the two real questions. The first one is, of course, turbulence is not detrimental if you match the wavefront, okay? We use a setup very similar to what was described before, and we came independently to this idea to use, let's say, a 4F system that is a perfect relay of the beam that is coming here is perfectly relayed here. Okay, so you can image the system, and after the second B splitter, the two beams perfectly overlap. Okay, and you can here see, for instance, this is the image of the primary mirror of the telescope that was imaged with a camera here in this point, and you can see that by blocking one arm of the other, the image is completely the same. So the beam completely overlap here. And also, it's very important to say that since the turbulence scale, okay, the time scale of the turbulence, if of the order of, let's say, millisecond scale, okay, if the time being is, the distance between the two time being is very short, like 3 nanoseconds in our case, you don't care about turbulence, because essentially there is no way that turbulence can change between one being and the other, okay? So this is the main motivation. The main trick is to match the waveform, okay? And the other question, okay, here you can see a picture of the interferometer. And the other question is, okay, can we use time being with the moving object, okay? And yes, if you take into account what we call the dynamical phase, okay? What is such dynamical phase is this following, okay? You have these two time beings, okay, separated by 3 nanoseconds, one after the other, and the satellite is moving, okay? And the satellite is moving very fast. The LEO satellites are moving up to, let's say, 5 kilometers per second, okay? With such velocity, it means that between the first pass and the second pass, the satellite is leaping away, okay? If you do the calculation, in 3 nanoseconds, the satellite is moving of tens of microns, okay? Tens of microns, okay, means that the phase relation between the two passes are changed, okay? This is a kind of Doppler effect, okay? So you need to take into account that the satellite is moving, okay? And if you take into account this, you can calculate what is the phase shift that is due to the satellite motion, okay? And this phase shift changing during the passage of the satellite, here you can see the radial velocity. What matters is just the radial velocity of the satellite, from, let's say, -6 to +6 kilometers per second, okay? I would like to stress that this effect is not just an effect on the, let's say, plug and play or two-way scheme, but it's an effect that you have to take into account in any one-way communication, okay? If you have one object that is moving with respect to the other, you need to take into account this phase for time being encoding, okay? And in our scheme, we send the path and we reflected by the satellite. This satellite is introducing this phase shift, okay, and then the light is reflected back and passes to the same interferometer that we use in the uplink. And this trick allows to have a self-stabilized interferometer, okay, so the light passes through the same interferometer once and back. So we didn't stabilize the interferometer for such a reason. And indeed, you can measure at the receiver, you expect 3 peaks of time of arrival, and you expect that the central peaks, the counts at the central peak will vary according to the predicted phase, okay? If you have interference, okay? So, in a typical passage of a satellite, you can see here, these are the distance, okay? And you can see here what is the phase that is this dynamical phase that was added by the satellite. And this phase can go from, let's say, -400 to +400 radians, okay? So it's a huge phase that you need to compensate in order to retrieve the right interference. And indeed, this is just a theoretical calculation, if you plot the probability of detecting the photon in the central peak and the interference peaks, you see a modulating interference pattern depending on the position and the velocity of the satellite, okay? And here there is a term that is related to the, let's say, theoretical visibility that essentially is related to the physical delay between the paths. But in our case, this delay is much shorter than the coherence time of the pulses, so this visibility, the theoretical visibility at least, is of the order 1, okay? So what we did is the following. We use satellite laser ranging to precisely determine this, the ranging, okay, the distance of the satellite. From the distance, you can measure the velocity of the satellite, okay? So you can predict in each distance what is the phase that the satellite introduces on the time being, okay? And then you see the data, okay? These are the typical histograms, okay, that we measured in three cases. Okay, this is the case in which we have all the data. Okay, we took all the data from the full passage. Okay, and you can see here that the interference is completely spoiled. There is no interference at all, and the central peak is the double of the two lateral peaks. Okay. On the other hand, if you select the precise moment in which you expect a constructive interference or a destructive interference that correspond to the phase 0 or pi, you can clearly see that the interference effect is present. Okay? Here you see a constructive interference, and here you see a destructive interference with respect to the no interference case. Okay? And we did this measurement for 3 different satellites, selecting different phase shift from the satellite. We measured a modulating pattern of this probability in function of this dynamical phase introduced by the satellite. Okay? So you can clearly see that there is a modulating pattern of the interference. And the visibility that we achieve is up to 67%. And this is not due to the interferometer itself, in the sense that the interferometer behaves quite well. The lab measurements are of the order, let's say, 95% visibility. The main issue is related to two stuff. One is the perfectly matching of the wavefront, so this could be improved. These are working on that. And also, can be improved by further stabilizing the interferometer, because as I told you, the interferometer is self-stabilized. But since let's say, the time delay between the outgoing pulse and the going back pulse are of the order, let's say, 10 milliseconds, okay? If the vibration of the interferometer are faster than this 10 milliseconds, then the visibility is decreased, okay? So, sorry for, okay. So, the next step will be to active stabilize the interferometer to compensate also for such fast drifting of the interferometer, okay? So, in summary, what we have demonstrated is that it's possible to have quantum communication with polarization encoding from the satellite, okay? With the low Q bar compatible with the quantum key distribution. And also, is it possible to extend this scheme of plug-and-play scheme with the satellite up to MEO satellite at such distance? The record distance is 7,000 kilometers. But also, in this last experiment, we have demonstrated that also time-being encoding is suitable for long-distance free space communication, and that if you take into account the relative motion, you can completely derive the phase that you expect from the satellite. And one thing that we are working on is to extend such scheme to farther distance, and in particular toward geostationary satellite. And the critical issue is to achieve a better synchronization. If you achieve a better synchronization, then you have a better resection of the background, so you can improve your capability to detect the single photon from the satellite with respect to the dark current. Okay, and as a general comment, such the ability of propagating quantum state over such long distance have a great impact not only for application, but also for fundamental physics, for understanding quantum physics and quantum correlation at a very deep scale, and also to fully understand the relation between quantum physics and general relativity, because you can imagine to test some general relativity effect on such photon state. So let me thank you for your attention, and these are the recent list of publications. Thank you.
Thank you, Pino. Any questions?
So, Dr. Dio, this would help, I guess, because you don't have this fast motion.
Yes, also, yeah.
Right. I mean,
yes,
okay, you have some motion, but the distance of satellites to your ground station remains the same.
Yes, yes. So the distance is almost the same. So because the Earth is moving, so okay. But if it's really geo of the same distance, you don't have this effect on the time being encoding. You're perfectly right. But of course, the losses are much. What really matters is the relative distance.
Paul?
Yeah.
One more time. Okay, so you're hypothesizing that your lower visibility might be due to drifts in the interferometer, in the
Yeah.
path. I mean, presumably you could measure that quite easily with a long coherence length laser and just sending it in locally and seeing, do you have drifts?
Yeah, yeah. Indeed.
Are there drifts on that scale? Or
Yeah, indeed there are. There are. So we did this measurement after the experiment to really characterize the setup, and indeed there are some fast measurements that could be removed by redesigning the interferometer. So we know for sure that there are some issue related to such high frequency fluctuation of the interferometer.
Okay, cool.
All right, let's thank the speaker again and all the speakers of this session.